crash course. Today we want to talk about decision trees. So we want to talk about decision trees, which are a very important family of classification algorithms, and they are pretty popular when it comes to ensembling decision trees that we will see. Random forest uses decision trees as basic classifier. Okay, but before that, just for who wants to work more with hidden Markov models or Bayesian network or Bayesian networks. For hidden Markov models, there is a package for those who want to do classification or having more experiments with hidden Markov models, and actually you could use that, but I think that it is enough that what we covered in the course. But if somebody wants to do some practical examples, in here actually there is a package for working with Markov models, and yeah, and also for Bayesian networks. There are different packages in Python. We do not use so much practical examples on Bayesian networks. They are really important and good to know in theoretical aspects, but in practice, inference from Bayesian networks are time consuming, so we prefer actually to use deep learning, which we will learn later. So but just for sake of knowledge, we taught you the Bayesian networks and hidden Markov models, but actual hidden Markov models are very useful for some time series recognition, or like speech recognition or action recognition, and so you could use them. Okay, anyway, so now we want to talk about decision trees. Okay, it is actually very good and easy topic to understand, so don't worry about that. Let's see first with just an example of decision trees, then I will explain the topics on this decision tree. Okay, let's say we have a decision tree like we have cylinders in here. If we have 3, then we classify that as good. If it is 4, then we will take a look at maker. If maker is USA, then it is bad. If it is Asia, it is good. Or if it is Africa, again, it is good. Then for 5, it could be bad. For 6, it is bad. And for 8, we could split on horsepower. If it is low, is bad. If it is medium, then it is good, and if it is high, then it is, let's say it is bad. So this is an example of decision tree. So it's pretty straightforward to infer the information from the decision tree. Actually, decision trees are human readable, and so it is really easy to understand what is this decision tree. We call actually these as leaves. So one of these is called leaf. So it means that each leaf assigns a class y. So in here, y is good or bad. So a leaf assigns a class y to here. Okay. To classify a new input, so when we have a new cylinder, then we want to know that it is good or bad, then we start from root. We call this root, and then we will go toward the leaves till we actually end up to one leaf. So for example, if I have a cylinder that is 8-cylinder, and the horsepower, let's say it is medium, and I want to know that whether it is good or bad. So in this case, I will start from here. Then I know that it has 8 cylinders. Then so I will go here. After that, I will look at horsepower. It is medium, so I will go here, and I will end up to good as a leaf. And so this is the way of inference in decision trees, and one branch for each possible attribute value. So in here, this branch is for the attribute of cylinder is 3. This means that the this attribute or feature, which is a number of cylinders, is 4, and so on. Okay. Now the question is, how should we learn a decision tree? So now we know that reading a decision tree is pretty straightforward. Now we want to know how to learning decision trees. Okay. So the question is, we should actually, let's say we have a data set that has some different attributes or different features. So to build a decision tree, we should actually choose an attribute. So if our data set, in this case, we have cylinders as attribute, we have maker and horsepower. So it is like for each data, we have a 3-dimensional vector. So the question is, let's say we want to build this tree, and now I put the root in here. What should I choose to put in here? It could be cylinders, it could be maker, it could be horsepower. Which attribute is the best to put in here? The question is that. Okay. Or in a more concrete example, let's say in here we have 2 different attributes or 2 features, and the label is y. So the data set is like this: true, true, true. So you can think of true and false as 0 and 1. So true, 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 false, true, 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 false, true. And there are some replicate actually the data in this table. Don't worry about them. True, false, true, true, false, 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 true, false, and again false, false, false. Okay. Now in this case, let's say we split on the attribute x1. So if we split on this attribute, then if, let's say, if it is true, then we say that y is true for 4 samples, right? So if x1 is true, that means that this one, this one, this one, this one, then in 4 case, here, 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 we have y equal to true and y is equal to false in actually when we have true x1, we don't have any y equal to false, so it is 0. And when it is false, then y is equal to true is 1, because in here means that when x1 is false, means that this one, this one, this one, and this one, and y is true in just one case in all of these 4 cases, and y is false in all remaining 3 cases. But if we split on x2, then for true we have y is equal to true for 3 cases and y is equal to false for 1 cases, for actually a case. So, and for x2 false, we have y is equal to true for 2 cases and y is equal to false for 2 cases. Hope that you now are able to count and understand that what are these numbers. So when we say that x2 is false, means that here, 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 and here. So in 2 cases, this case and this case, y is true, and in these 2 cases, y is false. Okay. Now, so the question is, would we prefer for x1 or x2 to split? Okay, so we want to answer this question, that how should we decide what variables should we choose to use in our decision tree. The idea, so the idea is actually to use counts at leaves to define probability distributions, so we can measure uncertainty. So if we want to know this split or this one is good or not, we could say that actually a good split, if this is a good split, if we are more certain about classification, after the split. So if this is the split, it is true or false. After that, I could say that, okay, now I'm more sure about that y is true or false, then I will be more certain about result. So if I could compare the uncertainty or certainty of classification after I split with these attributes, then I could decide this is more important, or this is a better attribute to split on, or this is better. So we should actually measure uncertainty after the split, or actually measure certainty. So we know that actually now probably you remember that we had something like this in information theory, that we called it entropy. Or in here it means completely uncertainty. Okay, and it is defined as for random variable y, it is defined as kind of average over all possible states, over actually the information of all possible states. So in this case, if we have a uniform distribution, then we will have a very high entropy. So it means that we actually, the uncertainty is very high and we don't know anything about the outcome. But if we have a very sharp distribution like this, then we will probably have a low entropy. So it means that we know approximately what is the outcome. So in this case, we know that the outcome is in this range. So the uncertainty is relatively low in comparison with this one. And if you remember that, if we have a coin, let's say we have a fair coin, means that the probability of head is y is equal to head is 0.5, or let's say this is p, and so the probability of y equal to tail is 1 minus p. So in this case, if you plot the entropy based on this p, then you will end up with something like this. And the maximum entropy is when the p is 0.5. It means that you don't know anything about which is more likely to outcome, head or tail. So they have equally spaced in your probability space. Okay, so we know that now more uncertainty means that we have more entropy. To review very quickly how to calculate the entropy, again consider this table. In here we want to calculate the entropy of, okay, let's see that on a new example. Let's say this is table x1, x2, and y, true, 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 false, true, 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 false, true, false, true, true, and false, false, false. Okay, so in here, now if you calculate the P of the probability of Y is being true, so it is this one, this one. So you have 1, 2, 3, 4, 5 out of all possible numbers, that is 6. And you have, so the probability of Y is being false is 1/6, and you could calculate the entropy very easy. So it is minus this probability times log of 5/6 minus 1/6 log of 1/6. It is 0.65. Okay, so this is how you could calculate the entropy. And actually, for using the entropy in decision trees, we should know another thing, which is conditional entropy, that I think we learned that also in information theory. That is the entropy of Y given X is sum over all possible states of X then calculate the entropy of Y conditioned on that state of X times log of this value. Right, so this is the conditional entropy that now we want to use this in decision trees. To see the example of that, now let's calculate the conditional entropy for x1. So we know that for x1 we had something like this. This one. Now the conditional entropy conditioned on x1 is minus 4/6, 1 log 2, 1 plus O log 2 O minus, and just note that we define this equal to 0, so because we don't have 0 in the log, so we define the limit, because we know that the limit of this is 0, so we define it equal to 0 minus 2/6, 1/2 log 2, 1/2 plus 1/2 log 2, 1/2. Okay, if you calculate that, you will end up with 1/3 as the conditional entropy of Y given x1. Okay, so now how should we use this entropy, which means that uncertainty, to choose the attribute for splitting? So we define a measure, we call that information gain. It is defined as decreasing entropy after splitting. So we want to know that how much uncertainty decreasing after the splitting. So this is the thing that important for us to choose an attribute. Okay, so it pretty makes sense to define information gain of an attribute as the uncertainty of the output variable before splitting minus the uncertainty of output variable given x. So this means that after the splitting, how much uncertainty we have, right? So for example, for x1, if you calculate that, you will end up with this, because we calculated this, and also this one we just need to subtract them. Okay, so now we could create an algorithm to train a decision tree. So the algorithm is to start from empty decision tree. So we have an empty decision tree, then split on next best attribute. When I write that best attribute, means that you should calculate the information gain, then choose the maximum x or attribute that has the maximum information gain, or in other words, you should calculate the argmax of information gains for different attributes, which is argmax of hy minus hy given xi. Okay, then you should recurse this. Okay, so again, it means that you split on one variable, then for this branch you select another attribute, another best attribute after this one, and so on. Okay, so this is the recursive algorithm. So every recursive algorithm needs some base conditions to stop. So because this actually goes to infinity, so we want to know that when should we stop this recursion. Okay, so we need some base conditions. The first condition, the first base condition, could be if all records in current data subset have the same output. So let's say you split the data, then now you see that all of the data after splitting have the same output variable. So all of them are true, or all of them are false. So in this case, you stop to again splitting this. The second base condition could be if all records have exactly the same set of input attributes, then we don't recurse. So what does it mean? It means that if we have the data true, let's say true, false, and we have another which is true, false, then we don't want to split on this attribute, because all of these have the same attribute. Okay, let's say it is not important, that it could be true, false, but if you want to split on x1, then it is true, true. So both of them have the same attribute. Okay, and maybe someone says that for another base condition could be small information gain. So is that really good idea to, if we get to some point that has very low information gain, then we stop splitting? But now we will see the problem of this idea. Let's say our goal is to the problem of XOR, which is, if you don't know, it means that, let's say we have A, B, Y in here. The XOR problem is, it means that 0, 0, then we want 0, 0, 1, we want 1, 1, 0, 1, and 1, 1, 0. Okay, so it is the XOR problem. Then in this case, if you use this rule, the input value, the input could be A or B, the value of A could be 0 and 1, the value of B could be 0 and 1. If you calculate the information gain for A, it is 0, and for B also it is 0. So you cannot create a decision tree because both attributes have very small information gain, or actually it is 0. But without that, without this condition, you could actually create decision tree that could split the space to classify the input. So the prediction is 0, 1, 1, 0. So if you see that, it has 100% accuracy on the training set. Instead of doing this, we will use pruning to make the decision tree smaller and to build the decision tree. Because so probably you now understand that decision trees will overfit, because let's see, an example of accuracy and size of trees. So when your data is splitted more and more, so it means that your size of the tree will increase, then your training accuracy will increase until you get the best possible accuracy, which probably is 100% if you don't have noisy label. So this is training accuracy. But if you plot the test accuracy, you will probably see something like this. So in here, this region, you have overfitting, which means that you have very good accuracy score on your training data set, but you have poor performance on the test data set. Okay, so this is actually the problem of decision trees that have zero bias for training data. In other words, they will get zero error on training data if you don't have label noise. So label noise, if you don't know what is that, it means that if you have something like true, false, let's say this is x1, x2, and this is the label. So let's say we have true, false, true, and again true, false, but false. So in here, if your test data or training data is true and false, if your classifier says that it is true, then it is wrong, because in here you also have false. If it says false, again in here we have true. So it means that we have noisy label in here. So if we don't have noisy label, then decision trees achieve 100% accuracy on the training data. So we will end up with very high variance. So we learned about bias variance trade-off. We make the bias very low, so we have very high variance. So what is the cure for this problem? The solution is we should actually introduce some bias towards simpler trees. So we should somehow create simpler trees. For creating simpler trees, one solution, for example, is to use fixed depth trees, or so it means that when we reach to certain depth, let's say it is 3, then we don't split anymore. So we will limit the variance of the classifier. Okay, or using minimum number of samples per leaf. So in this case, we use we say that we want to have some samples in each leaf, some minimum samples, okay, to reduce the variance. Or actually we could use a random forest, which we will see later. Okay, for this session, let's stop here. In the next session, we continue this discussion, and also we will see practical example on decision tree in the scalar, how to use that in scalar, and also we will introduce to random forest, which is very powerful method and popular method for classification. And you could use that in actually very different areas and competitions. And it is used actually widely as a classifier. Okay, see you in the next session. Bye.